So I thought it would be fun today to actually explain what hexadecimal is and partially what binary is to people who are unfamiliar with computers and really any numeric system other than Roman numerals or the decimal system. Which, if you're not aware, the decimal system is what almost every number is written in, especially in Western countries like America and Europe. Uh, I'm sure there are a lot of other popular number systems further to the east and possibly uh, the far north and south, but they're probably not nearly as popular as decimal or what Roman numerals used to be like. Remember, uh, during the days of the Romans, those were the only things I think were used, at least in the Roman Empire. But that's besides the point. Basically, what hexadecimal is just like decimal, only you have 6 extra characters for storing more information in a smaller space. So these are all just as they were before, but this is now 10, 11, 12, 13, 14, and 15. And so uh, in a number like this written in hexadecimal, this place right here is the 16's place, not the 10's place anymore. And so whatever is here is multiplied by 16, or say the single digit is multiplied by 16, and then the next one is multiplied by 16 times 16. So it follows the same model as decimal even in that way, only replace everything in that system regarding 10 with 16. And then that's basically hexadecimal. And if you follow those rules, you can deduce that this is 0, this is, let's see here, looking it up, 10, 11, 12, 13. This is 13 times 16. And what's 13 times 16? Hold on, let me do some quick mental arithmetic. 10 times 16 is 160, and then 3 times 16 is 48. 160 plus 48, that is 208. And so this value right here is 208. And so now you can begin to see the value of hexadecimal. The first value, that is. There's a second hidden value, but you can store a lot more information into a smaller space. And so actually here in this list we can see I've marked the powers of 2 in decimal here, a hexadecimal and binary, because the powers of 2 are very important in computing and just reality actually, only it's not really recognized that way very often, but that's besides the point. Wait, what was I saying? Oh yeah, every how far is it? I think it's every 5th power of 2 is the maximum amount of information you can store in that next digit, or in having that many next digits. So the maximum you can store in this is 256 different combinations, and then the next one after that, according to my memory, is in here, either this one here or I think this one here, probably this one though. And so that's a lot of information to store in only 3 digits. However, in binary, storing information is significantly more difficult because you only have 2 symbols, and so the number of possible combinations is significantly lower. In fact, adding another digit to your binary number only increments it up 1 in the powers of 2 for how big it can be, and that's where you get the weird things in computers like the integer. What was it called again? Well, there's a maximum size a number can be in a computer without needing to be stored in multiple bytes at a time. But the reason is because of this. And so for having 4 digits of binary, you have 8 possible combinations. No, wait, that's 3 digits. This here is 0 digits, actually, I'm pretty sure. And this is 1 digit, because I don't think I should go into that anymore for right now. Instead, I should go over here and I can start explaining some conventions for how this is all used. First of all, usually when you're talking about a hexadecimal number, you prefix the number with this symbol. And if you're talking about binary, it's prefixed with this symbol here, which is just a 0 and then an X, or a 0 and a B. Octal is similar, but it's just a 0 when doing octal. And octal is just like the rules for hexadecimal and binary, only forget the last 2 digits right here. Those don't exist anymore. Or then you only have 0 through 7, which is 8 characters to work with. And in binary, forget all of these. Now you only have 2 to work with. And there is actually a secret system called unary, in which you remove another one, and now you only have 1 character right here. And the way you get that to work is remember the tally system. Well, this is 1, this is 2, this is 3, 4, and 5. And so that's how unary works. Each symbol you add increments the number by 1, and decrementing the number is as simple as taking away 1 symbol. The problem with this, however, is that try storing 1,000. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah. And in decimal, there's 1,000 in decimal. So unary, you can't store large numbers with. It's just not possible. But in decimal, storing large numbers is relatively easy. And as you can see here, with hexadecimal, it's even easier. But over here, you can see a hidden strength of hexadecimal is it is super compatible with binary. And so for each digit over you move in hexadecimal, you move 1, 2, 3 digits in binary. And so I think it's each 4 digits of binary correlates to 1 digit in hexadecimal. So actually, I think this might be incorrect. In hexadecimal, I'm pretty sure this in binary correlates to about 10,000, or 10,000. If it were decimal, yeah, that would be 10,000. But this is actually counting it in the 1s, 2s, 4s, 8s, and 16s place. This being 16, and this also being 16, you can see where that comes from. It's just an occurrence that arises from how it works fundamentally. Octal, as I mentioned earlier, is another system. Wait, do I even need to explain octal? If you know about all these other ones, you can basically guess what octal is all about. You see, the main problem in using hexadecimal is you don't usually think in terms of hexadecimal, and nor do you speak in terms of hexadecimal. You speak in decimal. And by that I mean you actually specify in your speech the 100s, 10s, and 1s places. So if I were to say 150, that's specifying the 100s and 10s places, like this here. But in hexadecimal, if I were to say 255, that would mean... wait, what would that mean? Oh yeah, this is 255 in hexadecimal, I'm pretty sure. And this is 256 right here. And so you see, now there's no correlation between the digits and what you're saying. It's just a correlation in value. However, if you were to speak in a slightly different convention. Like maybe instead of using T as the end fix for the tens place, using something like maybe a tar, saying fifth tar. That would be in hexadecimal this value, which in decimal this times 16. That's pretty simple. I think that's 80. Yeah, so fifth tar in hexadecimal is 80 in decimal, and so you just need to change the way you speak in order to speak in hexadecimal, uh, as is logical, of course. However, in order to have a fully fleshed out system for speaking in hexadecimal, that would take some time to develop, and I doubt it would catch on very well or very quickly, since people are so used to decimal. In fact, the decimal system has been used for hundreds, if not thousands of years by now, from my memory. Uh, and so that's basically built into culture and civilization by now. However, the value of hexadecimal is clearly presented by its emergence in a almost purely decimal society, and that kind of just displays its power, that it can actually still be useful even with it being unpopular. Uh, what else is there to say about hexadecimal, actually? Uh, hmm. Another way you could represent hexadecimal I just now thought about is stacking four binary digits on top of each other and having this be one whole hexadecimal character, because that counts. And so that way you can read this in both binary form and hexadecimal form. So each 4 bits is one unique hexadecimal digit. However, that's also a very unpopular system for writing down numbers. Binary is actually more popularly known about than hexadecimal, since it's even more basic than hexadecimal and even more ingrained in computing, how computers work. Hexadecimal is actually just something that rose out of a need for a better numbering system in computers. Uh, and one very important reason why hexadecimal is more efficient in computers is in order to convert binary to decimal, you need something called a BCD converter, binary to decimal converter, which is actually a very complex algorithm that you need to apply to binary in order to turn it into decimal, which isn't necessary in hexadecimal because you just take each 4 bits and that's one hex digit, and then at that point you just decode it into whatever it's supposed to be. Uh, and that's the value of hexadecimal. And that's also why it's so compatible with binary as opposed to decimal, because decimal is actually one of the worst systems to try to mate up with binary, since it's so highly incompatible. You know what else is actually partially compatible with hexadecimal? No, wait, not octal. I think popularly it's called dozenal, uh, which is a system where you actually cut out these 4 extra and only have 2 extra symbols, so now you have 12 symbols. And so that works the same but with 12 symbols, which isn't directly compatible with binary, but it is partially compatible with hexadecimal. And the reason for that is, actually, I think the best way to explain it is just to show it. It's more compatible than binary, but not completely compatible. So in hexadecimal, I think I remember this being 12. Yeah, that's 12 right here, which in dozenal is just like that, like normal. I'm sure you already can guess. But the next one, adding 12 to that, uh, uh, that appears to be, I think, like this in hexadecimal, but I'm not sure. converting numeric systems is not something I'm very good at, and I can still do it somewhat proficiently. And so if I can do it, basically anyone can with some practice. Uh, but I think that's all you need to know in order to work with hexadecimal and binary. The very basic most or baser most information required. Uh, I recommend learning more about it though, since it's so interesting.